Hi, I'm Bill Bain. I'm with ScaleOut Software, and I'm going to talk about using big data analytics techniques to track 10 million cable viewers and provide operational intelligence in real time. So first of all, what do I mean by operational intelligence? I'm talking about using big data analytics techniques to provide immediate feedback to live operational systems and enhance the behavior of those systems. So here's some examples. Equity trading systems can use operational intelligence to minimize risk during a trading day. E-commerce systems can make personalized recommendations to shoppers as they're shopping. Reservation systems can find and identify issues with travelers, reroute them, solve those problems in real time. Of course, banking systems can use operational intelligence to find fraudulent transactions, wire transfers, credit card fraud. And of course, the topic of today is cable media. How do you track cable viewers, especially in the new market era we see in the announcements this week with HBO and CBS yesterday? The cable industry wants to be very effective in upselling their customers and providing the best possible viewing experience. So operational intelligence is a good tool for them to employ. Now, how does operational intelligence differ from business intelligence? Well, business intelligence is typically what you find with Hadoop MapReduce in the data warehouse. You're looking at very large, typically static data sets in the petabytes. You're providing analysis that runs for minutes or even hours to find long-term strategic trends. With operational intelligence, you're looking at live data sets, typically smaller, hundreds of gigabytes to terabytes, looking at fast-changing data to identify immediate patterns and trends on which you can feed back to a live mission-critical system to steer its behavior and provide enhanced operations. You can integrate these two views into one system, and we are talking with customers that take an integrated view of analytics because operational intelligence can be used at the periphery as data is flowing into the data warehouse to do two things. One is to provide immediate feedback to the point of sale, if it's an e-commerce system, for example, and then also to transform that data to perform ETL to put the data in the right format to store it in, for example, HDFS for use in a MapReduce, a Hadoop MapReduce data warehouse. So you can see that you could use business intelligence for strategic guidance while you're using operational intelligence for tactical real-time guidance to steer the behavior of the system. Now, some of the challenges you face in implementing operational intelligence are, first of all, how do you keep up with the fast update rate of the data? You have to be able to track a live system, update the state of that system, and do so in real time as a very large volume of updates flow in. You also have to be able to look for patterns and trends, apply analytics techniques in parallel typically, so that you can find patterns and trends and feed back to that system. So these are the two big challenges that we face. And the technique that we have employed and we find is valuable for users is to use InMemory Computing to address these challenges. Because InMemory Computing lets you track the state of a live system in memory and then perform parallel computation on the data in order to generate the feedback. Now, what's interesting is that you can view the state of the live system in memory as modeling the entities of the live system instead of modeling the events. So you find many techniques like CEP, complex event processing, and others, Storm, for example, are really focused on the stream of data as opposed to modeling the live system and updating that model with a stream of updates. So these entities could be, for example, shopping carts in an e-commerce system. They could be orders and inventory in a logistics system. They could be financial portfolios that you're tracking as market prices change. Or in the case of cable TV viewers, they could be the state of set-top boxes. What are people watching? How long have they been watching those shows? Now, our company builds what are called in-memory data grids, and this technology has evolved over the last decade, and in recent years, it's starting to employ integrated data parallel computation in addition to in-memory data storage. But it's a very nice platform for hosting operational intelligence because, first of all, it takes an object-oriented view of data. So if you're modeling a large population of real-world entities, you can choose an object-oriented view of that data and store them as an unstructured collection of objects. And then you can employ what are called create, read, update, delete, or CRUD APIs to update those entities in real time. It's this ability to individually update entities within the model that make this very suitable for operational intelligence. you can contrast unstructured collections of objects to resilient distributed data sets in Spark, and we'll talk more about that in a few minutes and how these two approaches are different and how they have different goals. Now, in-memory data grids take the data, the collections of objects, and they distribute them transparently across a grid of servers, provide integrated high availability through data replication. By doing so, they can scale both the throughput and also the storage capacity, as well as be providing a very nice platform for data parallel computation, which can be integrated directly into the grid on the same commodity servers. By doing so, you can generate very fast results because you're avoiding the batch scheduling overheads and, more importantly, the data motion that's inherent to moving data from disk into memory. And in fact, you're not moving data across the network because the grid servers are analyzing the data that's hosted on those servers. So the net result is you have very fast data parallel computation with integrated high availability, both for data storage and for the computation. Now, we use a technique we call parallel method invocation, which is really just an implementation of standard data parallel techniques from high-performance computing, going back about 20 years to the national labs. In addition, the more recent techniques like Hadoop MapReduce or even the Spark operators can be implemented on this kind of a platform. We, in fact, have implemented Hadoop MapReduce itself, and we can show you that if you're interested in how in-memory MapReduce runs with much lower latency than the standard batch scheduling approach that you would normally find in most deployments. And what's important is you can run MapReduce on fast-changing live data and thereby extract results using well-understood design patterns from MapReduce and other operators and do that in real time. So those are some of the benefits, and I might point out that Yarn has made it possible to integrate operational intelligence with business intelligence because it's capable of sending some jobs to the data warehouse and other jobs to the in-memory data grid for real-time analytics. And both of those jobs can draw data from the same HDFS store or from memory, or the in-memory computation can draw it from the grid as the data is changing. Now, just quickly, just to set the stage how we're a little bit different than Spark, Spark's goal was really to accelerate the MapReduce by using in-memory computation, storing the data in memory, keeping it in memory. And by doing so, it also can be extended to implement other data parallel operators, as you probably well understand. What's different, however, from the approach I'm discussing is that it's really designed really as a parallel data computation model, not as an object-oriented store, which allows you to access individual objects and update them to track the state of a system. So immutable RDDs are not as appropriate for storing the state of a live system as an in-memory data grid is because of the ability to do individual updates. In addition, the choices were made for performance relative to availability were in favor of using lineage instead of data replication. What we find is in real-time mission-critical environments where you have to have instant access to data, data replication is required. And that's, so for those reasons, for operational intelligence in live systems, the choices that are made by in-memory data grids are preferable. Now let's just take a quick look at cable viewers, which is the topic of this talk. So we're talking about tracking about 10 million cable viewers, doing about 2.2 billion channel switches and on-off events a day, or 25,000 a second. We learned this in working with a big cable company in the southeast US, and what they need to be able to do is to cleanse those events, to get rid of the people that fell asleep on the sofa or the channel switchers, find the relevant active viewers, correlate that and enrich it with programming data, and then send it to their highly proprietary recommendation engine so that an upsell offer can be made in real time. And they want to be able to do that in under 5 seconds. And with current technologies, it can take them up to 6 hours to do that. In addition, they want to look for aggregate statistics and see what are the most popular programs so they can generate offers based on how the population as a whole is behaving. So the architecture we chose, of course, is to use an in-memory data grid and to store the cable objects, the state of the cable systems themselves as objects in the grid, update them as the events flow in, and then enrich them and cleanse them using data parallel computation and generate events back to the recommendation engine and do so as quickly as possible. And what we have learned is that we could do this in under a second using these techniques that I've described today. In addition, we can capture aggregate statistics like most popular programs and do that in under 10 seconds. And we've now cut that in half to about 5 seconds. So you can see that in-memory computation provides an ideal platform for operational intelligence because of its ability to model a live system and to provide immediate feedback to that system. Thank you very much for your attention today.